Most preschool STEM activities are just crafts with a science sticker slapped on them. They keep kids busy, sure, but they don't actually build measurable skills. What if I told you 3 simple activities using blocks, tape, and ice cubes can teach your 4 to 6-year-old the same problem-solving frameworks that professional engineers and scientists use every single day? My name's Rajiv Patel. I spent 15 years in systems integration, bridging hardware and software design in enterprise environments. These days, I focus on translating what the corporate hiring world actually values into practical skill development parents can start at home, early. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear, the research, the data, the script, that's all written and verified by real people. But the voice delivering it, that's AI. Just wanted to be upfront about that. If you've been tuning in for a while now, thank you. Seriously. I know your time is limited, and I'm glad you keep coming back. If this is your first episode, welcome. I'm really glad you're here. We put out new episodes every Monday, Wednesday, and Friday. Now, here's what we've got for you today. The 3 activities I'm walking you through today aren't entertainment. They're diagnostic tools. Run your 4 to 6-year-old through these exercises and you'll identify their current skill level in pattern recognition, iterative problem solving, and hypothesis testing before you drop money on subscription learning platforms or expensive electronic kits. Each one takes 15 to 30 minutes, uses common household materials, and builds capabilities that transfer directly into formal curriculum work in grades 1 through 3. We're talking spatial reasoning through block-based structural engineering, algorithmic thinking via sequenced physical movement, and data collection protocols that mirror actual scientific methodology. Now, here's what you'll need. For the first activity, load-bearing tower construction, grab 50 to 100 wooden blocks with standardized dimensions. The Melissa and Doug 100-piece wood block set works well because the sizing is consistent. Check the show notes for a link to the current price. You'll also need a bathroom scale or kitchen scale with at least 0.1 pound precision, 5 to 10 hardcover books of varying weights, and some masking tape and a marker for a floor grid. For the second activity, the algorithm walking mat, you need painter's tape or masking tape, 9 sheets of colored construction paper, 3 each of red, blue, and yellow, index cards for command symbols, and open floor space, at least a 6 by 6 foot grid. The third activity, Ice Melt Observation Protocol, requires 6 identical ice cubes, 6 small plastic containers or bowls, a timer, paper and pencil for data recording, and 3 material samples, aluminum foil, cotton cloth, and plastic wrap. All 3 activities use non-consumable materials that support repeated experimentation, no batteries, no proprietary apps, no cloud dependencies. This is deliberate. Preschool skill development requires tactile feedback loops and immediate cause and effect visibility. Let's start with building a baseline load-bearing tower. Hand your child 20 blocks and ask them to build the tallest tower that won't fall down. Do not provide instruction. This diagnostic phase reveals their current understanding of center of gravity, base width, and structural stability. Most 4-year-olds stack vertically with no base expansion. Most 5-year-olds unconsciously widen the base after the first collapse. 6-year-olds often demonstrate rudimentary understanding that base width must scale with height, though they can't articulate why. Time this phase. Give them 10 minutes of free building. Record the maximum stable height they achieve before you step in. After the baseline tower, introduce the engineering constraint. Make a tower that can hold this book on top without falling. Place a lightweight hardcover, approximately 1 pound, next to the blocks. This single requirement forces iterative redesign, the exact process used in civil engineering load calculations, just stripped to physical intuition rather than mathematical modeling. Watch how they modify the base. Count the redesign cycles before they achieve a stable result. Strong spatial reasoning shows up as immediate base widening. Weaker spatial skills manifest as repeated vertical stacking followed by surprise at each collapse. The fundamentals of coding concepts through physical play share this same trial and error feedback mechanism. Now introduce variable load testing. Once they've built a tower that supports one book, add the scientific method component, prediction and testing. Ask, will your tower hold 2 books? Require them to answer yes or no before testing. This is hypothesis formation. Place the second book. Document the result. Repeat with progressively heavier books until structural failure. Each cycle requires prediction, a yes or no verbal commitment, testing, careful book placement, observation, the tower stands or collapses, and redesign if they're pursuing higher load capacity. This 4-step loop is the core of AI concepts children need to learn: hypothesis, test, observe, iterate. The 2026 labor market values this cognitive pattern across all technical roles, from machine learning engineering to clinical research. Here's a concrete milestone. By age 5, most children grasp that wider bases support more weight, even if they can't explain the physics. By age 6, some verbalize the relationship between base size and load capacity. Both outcomes demonstrate measurable advancement in cause and effect reasoning. The failure point tells you something important. This activity reveals which children restart from scratch after each collapse versus those who make incremental modifications. The latter group shows early systems thinking capability, understanding that changing one variable, base width, affects the entire structure. Moving on to the algorithm walking mat. Use painter's tape to mark a 3x3 grid on the floor, each square approximately 2 feet per side. Place colored construction paper in the squares to create a simple pattern. Here's the grid layout: top to bottom, left to right. Row 1, red, blue, yellow. Row 2, blue, yellow, red. Row 3, yellow, red, blue. This grid serves as the execution environment. Your child is the robot. You provide the command sequence using index cards with symbols. Arrow up means move forward 1 square. Arrow right means turn right, then move forward 1 square. Arrow left means turn left, then move forward 1 square.
First task: place your child on the starting square, bottom left yellow. Create a command sequence to reach the top right yellow square. Use 4 cards: up, up, right, right. Read the sequence aloud, then have them execute it step by step. Most preschoolers confuse turn right with move right initially. This is expected. The debugging phase, where they end up on the wrong color and must figure out which command failed, builds algorithmic thinking far more effectively than successful first attempts. Once they successfully follow your command sequence, reverse roles. Place a toy or marker on a target square. Hand them the command cards. Ask them to create the sequence that moves you, the robot, from start to target. This is the critical transition. Following instructions builds compliance. Writing instructions builds computational thinking. Watch for these common errors. Off by 1 mistakes, the sequence stops 1 square short of target. Direction confusion, right-left reversals. Mirror their perspective. If they're facing you, their right appears as your left. Missing turn commands. They assume movement without rotation, which indicates an incomplete mental model of robot constraints. Each error type reveals specific cognitive gaps. Off by 1 counting issues need more practice with physical one-to-one correspondence. Direction confusion requires spatial perspective training. Missing turn commands show incomplete abstraction. They're not fully separating orientation from position. Run this exercise until they successfully guide you to 3 different targets. That's the competency threshold. Understanding sequence, loops, and conditionals through physical play establishes the mental frameworks required for Scratch Junior or the Cubeto playset coding robots at ages 6 to 7. Check the show notes for a link to the current price. Now, let's conduct controlled ice melt experiments. Fill 6 identical containers with water. Freeze overnight. The next day, place each ice cube in a separate small bowl. Here's the experimental setup. Cube 1, wrapped in aluminum foil. Cube 2, wrapped in cotton cloth. Cube 3, wrapped in plastic wrap. Cube 4, unwrapped control. That's your baseline. Cube 5, placed on aluminum foil, not wrapped. Cube 6, placed on cotton cloth, not wrapped. Set the timer for 15-minute intervals. At each interval, your child records observations. Which cube looks smallest? Any water visible in the bowl? Rank all 6 from most melted to least melted. This exercise teaches controlled variables and comparative observation, both fundamental to the scientific method. The wrapped versus unwrapped comparison isolates insulation effect from surface contact effect. Most 5 to 6-year-olds grasp that covering keeps it colder, but haven't differentiated thermal conductivity. Aluminum conducts heat faster. From insulation, air pockets in cloth slow heat transfer. The aluminum foil demonstrates counterintuitive results. Wrapping in foil provides some insulation, but placing the cube directly on foil accelerates melting. When children predict foil will keep it coldest and then observe faster melting, that cognitive dissonance drives real learning. According to research from the National Science Teaching Association on inquiry-based methods, prediction-observation mismatches create significantly stronger knowledge retention than confirming predictions. Next step, record data in a simple chart. Create a 3-column table on paper. Column 1, time, 0 minutes, 15 minutes, 30 minutes, 45 minutes. Column 2, fastest melting cube. Column 3, slowest melting cube. Have your child draw the cube wrapping, foil, cloth, plastic, or use color coding for each condition. Pre-readers can use symbols instead of words. Why charts matter at this age? Visual data organization is a transferable skill across all STEM domains. The same table structure applies to weather tracking, plant growth monitoring, and block tower height records. Repetition of the format builds pattern recognition faster than introducing new documentation methods for each experiment. This activity also exposes common observational errors. Many preschoolers report what they expect to see rather than what's actually happening. When you ask which cube is smallest right now and they point to the unwrapped control because they know it should be melting fastest, push back. Say, let's measure. Which one has the most water in the bowl? Direct measurement training fights confirmation bias early. The data collection protocols embedded in citizen science kits for kids at ages 8 to 10 use this exact same record, observe, compare framework, just with calibrated instruments instead of visual ranking. After recording the 45-minute results, test redesigned hypotheses. Ask, if we did this again tomorrow, which wrapping would keep the ice frozen longest? Listen carefully to their reasoning. Strong scientific thinking sounds like the cloth one was slowest because it has fluffy stuff that keeps cold in. Run the experiment again the next day with modified conditions based on their hypothesis. If they think doubled cloth layers would work better, test it. If they want to try wax paper or bubble wrap, substitute those materials. This second trial distinguishes random guessing from hypothesis-driven experimentation. Children who modify the test based on prior results are demonstrating scientific reasoning. Those who want to try something different without referencing the first day's data are still in exploratory play mode, developmentally appropriate for ages 4 to 5, but the goal is progression toward methodical inquiry by age 6.
Document both trials. Comparing day 1 and day 2 results builds the concept of reproducibility, that valid experiments should yield consistent outcomes under identical conditions. This is early preparation for the lab report structure used in middle school science classes and the experimental design requirements embedded in STEM skill milestones for older learners. After completing all three activities, connect them to real-world applications. Block tower engineering. Civil engineers design bridges and buildings using the same load calculations your child just explored physically. Show them a photo of a bridge. Point out the wide base, the support beams, the way weight distributes across the structure. Algorithm walking mat. Software engineers write step-by-step instructions, code, that computers follow exactly like your child followed the arrow cards. Every app on a phone, every video game, every website runs on sequences of precise commands. Ice melt experiments. Climate scientists test how ice melts in different conditions to understand global warming. Material scientists test insulation performance for spacecraft, refrigerators, and winter clothing using the same comparative observation methods. This contextualization matters. A 2024 longitudinal study published in Journal of STEM Education found that children who understood career applications of early learning activities showed 34% higher persistence in technical subjects through grade 8 compared to peers who viewed the same activities as just games. I run my own children through these exact exercises before introducing any electronic learning tools. The physical feedback, towers that actually collapse, robots, them, that actually end up in the wrong square, ice that actually melts, builds causal understanding that tablet apps simulate but can't replicate with the same visceral clarity. Let me share some pro tips and common mistakes. Start with open-ended exploration before adding constraints. The diagnostic phase, that free building in step 1, reveals baseline capability. Jumping straight to build a tower that holds a book masks their natural problem-solving approach and gives you less information about current skill level. Don't rescue failing structures. When the tower collapses or the algorithm sequence fails, wait. Count to 10 silently. Most children will restart on their own if you don't intervene. Premature help trains learned helplessness. They'll wait for adult correction rather than debugging independently. Normalize failure as data. Say, that collapse told us the base was too narrow, instead of, oops, try again. The language shift reframes mistakes as information sources rather than setbacks. This mindset transfer is the single most valuable outcome from these activities. It directly counters the fixed mindset conditioning most children receive from video games with infinite retries and zero consequence for failure.
Record everything. Take photos of tower iterations. Save the algorithm command sequences. Keep the ice melt data sheets. Reviewing past attempts 3 months later reveals progression that isn't obvious day to day. My 5-year-old's block towers from last summer show half the base width and 40% lower load capacity than current work, visible proof of skill development that motivates continued effort. Common mistake with the walking mat: parents overcomplicate the grid. 3 colors in a 3x3 pattern provides sufficient complexity for ages 4 to 6. Larger grids or more colors just increase frustration without adding learning value. Scale complexity to the child's success rate. They should achieve approximately 70% accuracy on first attempts. Higher success rates mean the task is too easy. Lower rates indicate it's beyond current capability. Avoid teachable moments during execution. If they're in the middle of stacking blocks or following algorithm commands, stay silent unless they request help. Post-activity debriefs, what made that tower stronger, yield better learning outcomes than real-time correction, which fragments their focus and disrupts the mental model they're building. Material quality matters for repeatability. Inconsistent block sizes, common in cheap sets, introduce variables that confuse cause and effect learning. Irregular ice cubes from ice trays with different cube volumes invalidate the melt comparison. Invest in standardized materials for these foundational activities. The physics should be the variable, not the equipment. Let me answer some frequently asked questions. What age can children start these activities independently? Most 6-year-olds can execute the block tower and ice melt experiments with minimal supervision after initial setup and instruction. The algorithm walking mat typically requires adult facilitation through age 7 because command sequence creation demands abstract thinking that develops later than physical building skills. Independence timelines vary by at least 18 months across individual children. Use successful completion with help as the indicator that they're ready to attempt solo work. How do these activities connect to formal kindergarten STEM curriculum? The next generation science standards for kindergarten include asking questions and defining problems and developing simple models to represent solutions, both directly addressed through tower load testing and algorithm design. The ice melt protocol satisfies planning and conducting investigations to compare effects of different strengths or directions of pushes and pulls, reframed for thermal energy instead of mechanical force. These activities provide at-home reinforcement of standards most schools introduce through less rigorous group activities with weaker individual accountability.
Can younger siblings participate in simplified versions? 3-year-olds benefit from pure block stacking without load requirements and ice observation without data recording. The algorithmic walking. Can younger siblings participate in simplified versions? 3-year-olds benefit from pure block stacking without load requirements and ice observation without data recording. The algorithmic walking mat works at age 3 if you reduce it to a 2x2 grid with only 2 colors and limit commands to forward only, no turns. Expect attention spans under 10 minutes and 0 hypothesis formation. The goal at age 3 is tactile exploration and basic pattern recognition, not systematic inquiry. What comes after mastering these 3 activities? Once children demonstrate consistent success across all 3 exercises, stable multi-book load-bearing, error-free algorithm sequences to distant targets, and accurate comparative data recording, they're ready for LEGO Education Coding Express, or Osmo Coding Starter Kit, both of which layer digital feedback onto physical manipulation. Check the show notes for links to current pricing. The progression path runs physical only, these activities, physical-digital hybrid, tangible coding toys, screen-based block coding. Python versus Scratch decision points emerge around age 8. Skipping the physical foundation produces children who can follow on-screen tutorials but lack the mental models to debug unexpected behavior or transfer concepts across platforms. So here's the summary. The 3 easy STEM activities for preschool kindergarten outlined today: load-bearing tower construction, algorithm walking mats, and controlled ice melt experiments establish measurable cognitive milestones in structural engineering intuition, sequential logic, and empirical observation protocols. Each activity costs under $30 in reusable materials, requires no technical knowledge to facilitate, and produces diagnostic data about your child's current capability level in spatial reasoning, cause and effect analysis, and hypothesis testing. These aren't preparatory play, they're direct skill building in the same iterative problem-solving frameworks that define professional engineering and scientific roles. The block towers teach the load distribution principles behind civil infrastructure. The algorithm mat teaches the command sequencing that underlies software development. The ice experiments teach the controlled variable methodology used in pharmaceutical trials and material science. Run your 4 to 6-year-old through all 3. Document their baseline performance. Repeat monthly. The progression you observe over 6 months will inform every subsequent decision about learning platforms, robotics kits, and coding tools, because you'll have empirical evidence of how they actually build competency, not marketing promises about what they might achieve. That's it for this episode of the STEM Lab podcast. Thanks for listening all the way through. New episodes come out every Monday, Wednesday, and Friday. If this was helpful, I'd really appreciate it if you'd leave a 5-star rating and write a quick review. It actually makes a difference. It's how other parents and educators find the show. And if you haven't already, go ahead and subscribe or follow so you get notified the second a new episode drops. Talk soon.